So once again, good afternoon, everyone. Happy Wednesday. So today is Wednesday, April 14th. So a couple of announcements. So turn in your Chapter 17 homework next Monday, so you can have the weekend to go over those homework problems. Hopefully I'll finish Chapter 17 today, and I'll put in those 10 points once you upload it. Work on Quiz 4. Okay, so do not procrastinate on that. Lab report. There's one on spontaneity that I'd like for you to turn in. Otherwise, come this Friday and do the lab with us and turn the lab report in the following week. And also another lab report on your problem set. So turn that in as well, and I'll put in the 100 points, provided you do everything, you checked your answers and everything. So 2 lab reports that you guys should start working on. This one should be done. This one, once you do the lab, you can do the lab report. And so if you're still doing that clutch prep, make sure you do all those exercises. That should help you sort of with the course if you're having difficulties with the lecture material. And if you do all the exercises, I will give you extra credit at the end of the class. Also, for those of you that are coming to the lab, make sure you update your lab notebook like before. Same thing as in Chem 1. Turn in your lab notebook and I'll give you 100 points at the end of the semester. Right, so with that being said, let's go ahead and start Chapter 17. Or continue with Chapter 17. I want to explain to you guys this equation here, delta G equals delta G naught plus RT natural log of Q. So this is another equation. I'll give you this equation on the exam, but it may be good to know, be familiarized with it, especially if you're taking MCAT or all these other types of board exams. First of all, I'd like to bring your attention to Q. Okay, Q means one thing. It means that we are in an equilibrium. Remember equilibrium, the back and forth arrow? Okay, a reaction that does not go to 100%. So we're really talking about an equilibrium reaction. And for an equilibrium reaction, the reaction, just any reaction here, it has the back and forth arrow, remember? Okay, it does not go to 100% one way, and it doesn't go 0% one way. It's somewhere in the middle. Okay, so the equilibrium is sort of, which way does it favor products or reactants really depends on the equilibrium constant. So it really depends on the equilibrium constant K, right? But here, this equation has Q. So here, once again, just to remind everyone, ourselves, we compare Q to K. We compare equilibrium constant Q to K to determine which way the reaction will shift to establish equilibrium. So we compare Q to K to determine which way the reaction will shift. In order to establish equilibrium. So remember, we always put Q first, otherwise what I'm explaining to you is going to be wrong. But as long as you put Q first and then K second, we have a situation where Q will be greater than K. The alligator jaws are pointing to the left, so the reaction is going to shift to the left. to the reactant side. The other scenario, if Q is less than K, the alligator jaws point towards the product side, so the reaction will shift to the right in order to establish equilibrium. Which is the products. And then finally, if Q is equal to K, it's kind of like 50-50. If Q is equal to K, then there's really no shift. The reaction is at an equilibrium. Either equilibrium is, this way or this way. It's settled. Okay, it's going to be settled. And whatever the equilibrium constant is, it's settled. Either more products than reactants, or more reactants than products. The reaction is settled. It's not going to shift any way whatsoever. So here we call that scenario an equilibrium. Okay, so that's where this Q comes into the context of this equation. Also, another point I'd like for you guys to explain, or for me to explain, is that this equation has delta G naught. You see that little symbol there? That means naught. And that means standard state. So here we do sum of the products minus sum of the reactants. So this is standard state. And what are we trying to get? We're trying to get delta G of the reaction. This is not standard state. Not. Okay? So temperature, I don't know, 50 degrees. Pressure, I don't know, some pressure, some concentration. So this is not standard state. Take off the lights here. So one other thing I want to tell you guys on this equation, let's say your Q does equal to K. Okay? If your Q equals to K, it turns out that your delta G is equal to 0. Okay? This is non-standard state. This is when Q is equal to K, you are at equilibrium. So the reaction is settled. Okay, either this way, more products, either this way, more reactants, whatever. Q is equal to K, you are at equilibrium. But that also means your delta G is equal to 0. Right, so this gives us another equation that I'd like for you guys to recognize. I'll give this also as well, but if you're at equilibrium, put this down here. Remember, if you're at equilibrium, Q is equal to K. That means the reaction is not shifting anywhere. It's already settled. Okay, and delta G is equal to 0, so that means 0 equals delta G naught plus RT. Remember, Q is equal to K, natural log of K, which also means that now we are at equilibrium. Let's move this RT, natural log K, to the other side. This is our next equation. Delta G naught is minus RT, natural log of K. So this is our second equation. Now I'll give this also on the exam, but like before, like this one, it would be good to know. Okay, especially if you're taking MCAT or any of these other big exams that are heading your way. Okay, so this is at standard state, where it's all about K, equilibrium constant, and this is non-standard state, where it's not at equilibrium and you're not at 25 degrees and you're not at 1 molar and you're not at 1 atmosphere if you're talking about a gas. So notice, non-standard state, here's the equation. Standard state, here's the equation. Okay. So let's just put here standard state. Do we remember what standard state is? It's, I hear it, 1 molar if you're talking about a solution, a temperature of 25 degrees C. And if you're talking about a gas, if there's a gas anywhere in the reaction, the pressure is 1 atmosphere. So here we have a non-standard state equation for delta G. Here we have a standard state equation for delta G. And remember, delta G stands for Gibbs free energy. Gibbs free energy. This delta G, this Gibbs free energy, ultimately decides whether the reaction is going to go forward or not. It takes input from delta H. Sometimes the temperature can make the reaction move forward, and it takes input from delta S. So if a reaction is entropically favored, and if the reaction is entropically favored, as well as enthalpically favored, then the reaction is going to move into product side. And also the same, this equation also holds true for standard state. And then finally, I'd like to tell you guys that if a reaction is going to go to products, the delta G is going to be negative. That means, yes, the reaction is successful going to the products. It favors the products. Okay, whatever value of that energy, that delta G should be a minus sign. We also call that an exergonic reaction. Okay, just some vocabulary, that's all, an exergonic reaction. If you take biochemistry or any other type, maybe thermodynamics, I think it's offered here, thermodynamics. It's like a 4,000 level course. For chemistry majors, you go more into this. And if your delta G is positive, we call that an endergonic reaction. Reaction that does not go and favor the product side. In fact, you must add energy for this reaction to proceed, correct? Is it not so? You must add energy for this reaction to go and get to products. Here, if it's negative, it releases free energy, and actually that free energy can be captured and harnessed and utilized for something else. Okay, we see this all the time in biochem. So a couple of equations here. Make sure you know how to use them for the exam. Make sure you have familiarized yourself with this Gator rule or Q rule, comparing Q to K. Here's a table here. So the question that we want to ask ourselves is, will the reaction go? Okay, so the question, will the reaction go to products? Good question. Will the reaction go to products? Well, there's 3 things here. One is K. Well, there's 2 things here. There's K, and then there is delta G. Okay. Since we're at delta G, we can say delta G at standard state. Okay. So if your K is very much positive, remember, the example is if you have $1 million, even though K is unitless, let's say you have $1 million. Are you moving forward in life? Yes. If you have an equilibrium constant that's 1 million, you're moving towards the products. Okay, so that's shown here. If your K is very, very large, the natural log of K is very positive. If you're very, very large in terms of your K, that means from energetic from an energetic standpoint, you're exergonic. Exergonic because you're favoring the products. You will release energy. You will favor the products, and more often than not, you will release energy. So in this scenario, the products are favored. Okay. The opposite scenario, let's say your equilibrium constant is not 1,000,000, okay, but something very, very small, okay, itty bitty itty, okay, tiny, tiny, tiny number. The tinier the number, the less likely you are going to be favored to the product side. The smaller the number is. We've actually seen, and we've done problems where the equilibrium constants were 10 to the minus 6, 10 to the minus 7, 10 to the minus 10. In fact, we can do low ionization assumption if it's an acid-base problem. Remember, we did some assumptions to reduce our complexity. So if your K is very, very small, you're not really going to go to the product side. You're going to stay and remain in the reactant side. And that also means, just by natural log math, your natural log of K will be negative. But most importantly, your delta G will be positive. This is an endergonic reaction, a reaction that's not really moving forward. It's going to stay at the reactant side. Okay. And then finally, if your K is 1, you're not favoring the products, you're not favoring the reactants, you're kind of like 50-50. And in terms of a delta G naught, that's 0. And you're at an equilibrium. The reaction has settled. Okay? Reaction has settled to an equilibrium. So when I say an equilibrium constant is equal to 1, that doesn't mean 50-50. It just means the reaction is not going to move. Okay, it's going to stay like this, it's going to stay like this. Either more products, more reactants, okay, whatever it favors. If the equilibrium constant is 1, there's no shift. Okay, it's settled. Okay. Reaction has settled. All right, so here's somewhat of an important point here. We want to establish equilibrium. So in order to establish equilibrium, delta G is the one that changes. You see, this delta G naught is constant. We get the values from the back of the book. So that really doesn't change. If you don't understand this, it's really okay. But the idea is that delta G will always be this, standard state. It will always be sum of the products minus sum of the reactants. Sum of the products minus sum of the reactants. So that's really not going to change. What changes is this value, delta G, to get to equilibrium. See, we get the values from the back of our textbook, so this doesn't change, standard state conditions. What changes is this delta G. That changes to establish equilibrium. We see this all the time in all the reactions that happen in our cells. It's at delta G that we're worried about, because at standard state, we can calculate it, from using the textbook values, very specific set of conditions. There's a delta G that's going to move around and change accordingly to establish equilibrium. So this delta G that's going to move until you have equilibrium. The delta G naught just stays the same because these are values that are computed from the back of the book. Okay, so finally it is the sign of delta G that determines whether the reaction proceeds. The delta G naught, standard state, only tells us the relative amounts of products and reactants when equilibrium is reached. So to get to equilibrium, it's this delta G that actually moves around. All right, let's do a problem here. Okay, I think we have this problem and one more problem, and then we're finished with this chapter. comments or questions anyone would like to make? No? All right. So calculate the equilibrium constant Kp for this reaction. Okay, the reason why we have subscript P here, the P stands for pressure. So we have gas molecules, that means they have a pressure that's associated with them. So first we got the delta G here of O3, delta G naught. What does that tell you? It tells us standard state. Okay, anytime you see that little superscript O, okay, make sure we're talking about standard state. So let's calculate the delta G of this reaction. Shown here. It's going to be sum of the products minus sum of the reactants. All right, so we got a product here of 3 O2 gas. The enthalpy of formation of O2 gas is 0, so we can actually just and don't forget we multiply it by 3, but that's 0. So it's going to be 3 times 0 kilojoules per mole minus the delta G naught of O3. O3 is called ozone, is 163.6, but that's for 1 mole. How many moles do we actually have? 2. So products minus, put that big bracket in there, products minus the reactants. Well, we only have 1 reactant, so 2, because there's 2 moles, 163.6 kilojoules per mole. And then close that big bracket. By doing this on my calculator, I'm getting an answer of minus 327.2 kilojoules per mole. Okay, automatically that minus sign should tell you one thing, and that this is an exergonic reaction. Okay, how do I know it's exergonic? Because of the negative. Very good. Okay, so exergonic, which means this reaction favors the products. Okay, it favors the forward direction. So let's just remind ourselves the negative value is exergonic. All right, so we calculate delta G of the reaction, but we need to calculate Kp. So the equation we will use for that is this: delta G naught is equal to minus RT natural log of Kp. So the delta G of this reaction, we already just calculated it, right? So it's going to be minus 327.2. I'm not going to put units, because, why? Because K is unitless. Now, you can write the units in. They should all cancel each other, but, well, I'll put the units in. Okay, that's fine. I'll put the units in. But look, it's a minus 327.2 kilojoules per mole, right? So let's just make that joules per mole. All I'm just saying is K is unitless, so you really don't have to put units, but I'm going to add units in my final problem. 1 kilojoule is 1,000 joules, right? Is that right? Yes. Yes. Kg cancels. Kj cancels, so this is minus 327,000. Minus 327,123, 200 joules per mole. 1, 2, 3, yeah. Okay. So let's convert that to joules per mole, and now let's plug that in here. Minus 327,200 joules over mole equals minus R. Minus R is minus 8.314 joules over mole Kelvin. I'll give you R on the exam, so don't memorize it. minus R times T. What is T here? Okay, it's standard state, so what is the temperature at standard state? They even tell you it's 25 degrees, but yeah, correct. 25 degrees. Correct, right? So it's going to be 298 Kelvin. Yep. Natural log of Kp. All right, a couple of cancellation items here. This minus sign and that minus sign cancel. This joules over a mole cancels out with that joules over a mole, and this Kelvin cancels out with that Kelvin. Okay, so like I said, K is unitless. So let's do a little bit of math manipulation here. Minus 327,200. Like I said, the minuses and minuses cancel, but divided by minus 8.314 times 298, that equals to natural log of Kp. Okay. So let's get our calculators out. Hopefully I got my calculator now. I thought I had my calculator here. Well, I must have misplaced my calculator. Do you guys know how to do this on your calculator? So the minuses and minuses give you plus. So 327,200 divided by 8.314 times 298. So that's the natural log of Kp. Okay. All right, thank you so much. Oh, I don't know if I could use this. This is complicated. Yeah, this is one of those fancy calculators. Seriously. 327. 200. In case I got to back up. All right, I don't know where my calculator went, so I apologize about that. Divided by parentheses 8.314 times 298, close those parentheses, enter. So that's natural log of Kp. Okay, how do we get to Kp? We take the inverse natural log, and on Ariana's calculator, it's this button, not the natural log, but the inverse. So inverse natural log answer. Enter. 2.26 times 10 to the 57. Okay, we'll go with that. Okay. And that's Kp. Okay, don't forget you have to take the inverse natural log. All right.
It's a giant number.
Yeah. It's a giant number. All right, are we good?
So that would be KP, right?
That's the answer for Kp, yeah. Thanks so much. All right, so that is our answer. So Kp, is that a large number, 10 to the power of 57? Okay, it's massive. And what about this negative value? Okay, I guess you can call that massive. These two corroborate. Okay, that's what I want to tell you. These two corroborate. This is exergonic. A K that's so large, remember $1 million, are you moving forward in life or? This is moving forward as a reaction, and the minus, the negative delta G also should tell you that it's moving forward as a reaction. Okay, so the minus sign here, the huge number here for K, the exergonic delta G should tell you one thing. They corroborate with one another. The reaction favors the product side. All right, let's do our last problem here for this chapter. All right, so the Kp for the reaction N2 plus 3H2 goes to 2NH3. This NH3, by the way, is called ammonia. Okay, the Kp for this reaction, the reason why it's Kp is because these are all gases, and it's 4.3 times 10 to the minus 4. We quote the equilibrium constant at a specific temperature. In one experiment, the initial pressures are this, that, and that. Atmospheres, calculate delta G for the reaction. All right, well, first and foremost, we are not at standard state. Okay, if we were at standard state, this would be one atmosphere, but we're not. So this is non-standard state. Okay. Non-standard state. All right, because if we were at standard state, this would be one atmosphere, one atmosphere, one atmosphere. It's not. Also, this would be at 25 degrees. So the equation that we need to use is right here. Okay, this is the right equation. It's this one. Okay, and that equation is delta G is equal to delta G naught plus RT natural log of Q. Okay, Q. Let's first calculate delta G naught first. Okay, so step one, calculate delta G at standard state of this reaction. So let's remind ourselves that the delta G of the reaction is going to be sum of the products. Sum of the products minus sum of the reactants. So here's our equation one more time. So it's NH3. We got here the delta G naught values that are from the back of the book. So we have some of the products. So it's NH3 is minus 16.3 kilojoules per mole. We got two of those, so it's going to be 2 times minus 16.3 kilojoules per mole. Minus, so you're going to put a big bracket here, minus N2 gas, which is 0, okay, plus H2 gas, we got 3 moles of that, so it's going to be 3 times 0, which is just 0. The whole thing is 0. See that? Okay. All right, so doing this on the calculator, I'm getting minus 32.6 kilojoules per mole. Okay, just taking that times 2. All right, so these values will be given to you on the exam. All right, so that is delta G of the reaction. So that is right here at standard state. Okay, let's go ahead and calculate Q now. All right, so Q is going to be, here's our equation. I'll highlight it in orange. Okay, so Q is going to be the same equation as K. So Q is going to equal to pressure of NH3. What do we need to do with that pressure? We need to square it, right? Do we remember this from our last test? Right. Divided by products over reactants, divided by pressure of N2. What do we need to do with that? Raise it to the power of 1. Times the pressure of H2. What do we need to do with that? Cube it, right, very good. Raise it to the power of 3. Okay, this is the same thing as K, but we want to measure it relative to K, compare it to K is what I'm trying to say. So we got our pressures here. So NH3 pressure is 4.4 times 10 to the minus 3. We got to square that. Okay, squared. Divided by pressure of N2. They gave us a pressure of 0.86. Okay, so these Q's and K's, equilibrium constants, have no units. So I'm not going to bother myself with the units. And then pressure of H2, we got to cube that. 0.40, we'll cube that. Okay. So that is Q. And on my calculator, okay, you may want to double check this, but I'm getting 3.5 times 10 to the minus 4. Actually, Robert gave me a calculator, so I'll use that. Okay. 4.4 exponent minus 3. What? Oh, not this. I'll take that.
SD.
SD?
See, right
Got it. Okay, perfect, yeah. Oh, that's like, converts it to something weird, yeah. All right, so 4.4 times 10 to the minus 3. I gotta tell you, some of these calculators, like that engineering calculator, they're just so complicated. Squared, okay, divided by parentheses, 0.40, let's just do 0.40 times 0.40 times 0.40 as my way of cubing it. I know you probably have a better way. Times 0.86. And then we'll close that parentheses.
Oh my God.
3.5 times 10 to the minus 4. 1, 2, 3. Yeah, 3.5, 1 times 10 to the minus 4. There's a way you can program it. Oh, here we go. There we go, yeah. I think there's a way, Robert, you can do this so it just shows, instead of the fraction.
Some type of scientific.
Yeah.
Some mode.
There is a mode, yeah. Or you may have to reset it. Yeah, I can go on YouTube and figure out how to get it so it looks normal. I think it's this math thing. Yeah. Anyways, 3.51 times 10 to the minus 4. Maybe I'll just go a little extra digit here. 3.52 times 10 to the minus 4. Okay. All right. So that's Q. Remember, we compare Q to K. Obviously, it's not equal to K. What is K, by the way? Oh, yeah, K is, I'll highlight that in pink. So we're not at equilibrium. We're not at equilibrium. How do I know? Because that's K, and this is Q. Okay, so let's compare Q to K. Put Q first. So Q is 3.52 times 10 to the minus 4. K is given to us as 4.3 times 10 to the minus 4. And we can see here that K is greater than Q. Okay, here's the Q that we calculated under these pressures. Here's the K that is given to us, that is the equilibrium constant. Non-standard state. You see here the alligator jaws point to the right, so this reaction will actually go or shift towards the right to establish equilibrium. So the reaction shifts to the right. To establish equilibrium. All right, now let's go ahead now and calculate the delta G. Okay. Anybody want to guess whether they think delta G will be positive or negative? Remember, it shifts to the right, going to the product side. So what do you think it will be, positive or negative, this delta G now? It will be negative. Okay, if it's negative, that means the reaction shifts to the right. Exergonic. Okay. Anyways, let's see if it is indeed negative, right? So delta G, non-standard state, equals delta G naught. Delta G naught, we calculated it as minus 32.6. Let's go ahead and convert that to joules per mole, which is minus 32,600 joules over a mole. Plus RT. R, I'll give you R. It's 8.314 joules over a mole Kelvin. And what is T here? T is not 25 degrees. T is 375. Okay, so be careful. Temperature T is 375. What is that in Kelvin? We add 273 to that. It's 648 Kelvin. T. And then finally, natural log of Q. Natural log of Q, and Q is 3.52 times 10 to the minus 4. So doing all of that in our calculator should give us the answer for delta G under these conditions that are not standard state. All right, let's see if I can do this here. How should we do this? Well, you can break this apart individually. I may do it in one whole fell swoop. So let's see if I'm successful in doing that. Natural log of 3.52 exponent minus 4 is that times 648 times 8.314. Okay, that is that number, negative 42,840, negative, plus another negative, so plus a minus, you can just go with, minus 32,600, and I think that should be my answer. Yeah, minus 75,000. See, it's negative, exergonic. Q, the Gator rule tells us the reaction is going to shift to the product side, remember? So if it shifts to the product side, that means the delta G will be negative. So everything sort of checks. Together. So it's minus 75,440 joules per mole. Or you can say minus 75.4 kilojoules per mole if you want a less number of writing. instead of writing all those digits. Same thing. Okay. So the minus sign, exergonic. Exergonic favors the product side. And the Gator rule, or this Q rule, tells us it's going to favor the product side under these non-standard state pressures. Okay, non-standard state pressures. All right, so that completes Chapter 17. Make sure you do your homework. I filmed the videos for each of those homework problems to sort of guide you and help you. And then we'll start the last chapter of the course on Friday, which is electrochemistry. So have a good day, everyone, and I'll see you on Friday.